Professor Bjørnar Sandnes is now at the University of Swansea. He used to be here as the postdoc for quite a few years, and that was before many of you arrived. During that period, he produced the ProLab logo, rather the labyrinth from which the ProLab logo is taken. Is in a sense, in that sense, a founding father. So now things have developed, and you're still studying pattern forming processes, in this case, the viscously stabilized ones. So, Bjørnar, why don't you just start?
Okay, thank you very much for inviting me. I think it is a year and a half ago since the last time I spoke in the ProLab seminar series. So, I think last time we had a little geography lesson, because I think I told you that Wales is a separate country from England. This is very important. To know, we got Cardiff here is the capital, that's like Oslo, and I'm in Swansea. And you can think of Swansea, that's like Trondheim in terms of the size of the place. And the university is kind of similar in the sense that engineering has a proud history here. I thought I'd go a little bit further, so this was the geography. There's about 3 million people in Wales. I feel it's like my responsibility to tell all you good people back in Norway about all things Welsh. So 3 million people, it's a bit less than in Norway. It is a Celtic nation. So the people here are, they come from King Arthur and the Knights of the Round Table and all of those people. It is a land of the dragons and castles. And there you see some other famous Welsh people. We got Tom Jones and Gareth Bale. The modern day equivalents here. In Wales, we have our own language. So it is a Celtic language, and it is like nothing you've ever heard before. Bore da means good morning. And ur is this here. That means is their student discount. What you recognize is that there's a lot of Y's and W's and R's and consonants all over the place. And here is an actual place name in Wales. This is a train station. And Wales has got the record for having the longest place name in the world. And that's as you see it there. So that's the Welsh language, but here we speak, most people speak English, but up in the valleys and in certain parts of Wales, the Welsh language is still a live and active language. Right, so that was the Welsh contingency of this talk. Now on to the science. And this, some of you have heard before. So I'm going to basically summarize the things that we've learned about frictional fluids since I was a postdoc back in ProLab all the way until today. So it's going to be like a summary of the things we've learned. And basically, we are going to review experiments and simulations, but these are Hele-Shaw experiments. There are going to be 3 components to the system. There's going to be the defending fluid. There's going to be the invading fluid that we are going to pump in with a syringe pump at constant rates. And then in addition to those 2 fluids, invading and defending, we are going to put granular material inside the defending fluid. And the granular material is going to be wetted to the defending fluid. So we're always going to be in like drainage mode here. So that means that when the invading fluid comes in, the meniscus is going to push away the particles in the system. So that is it. And we're going to look at all the different ways that this displacement process can happen. So when we fill the cell, we can decide or we can control the filling level inside the cell. And we are going to operate with a filling fraction phi here, which is the ratio of the height of the filling of the grains to the height of the cell, where B here is the height of the cell. So when we inject, if the grains to begin with are suspended in a fluid that we inject into the cell, they are going to sediment out. They are typically glass beads in water, so they sediment out and they form a layer on this bottom cell. So that is the main design of these experiments. But first, let's think about what happens if there is no grains in the system. If this filling fraction here is 0, then we end up with just 2 fluids. So now we have a 2-fluid displacement process where we can inject one fluid into the other, and then it is well known that we get a viscous instability. We get viscous fingering when the invading fluid has the lower viscosity, and the defending fluid that is already there, that has got a higher viscosity. And that is because the pressure gradient becomes localized within the defending fluid, so that any finger of fluid that gets a little bit ahead of the others will accelerate because it feels a steeper pressure gradient. So this is at the heart of what gives you a viscous instability. Now, if we were to turn that upside down and inject the higher viscosity fluid into the low viscosity fluid, then we don't have a pattern forming scenario. We get a viscously stable displacement. So now the pressure gradient is in the side of the invading fluid, and therefore any bit that kind of falls behind gets pushed by a steeper pressure gradient and therefore catches up with the rest of the meniscus, and the viscosity here becomes a stabilizing mechanism. So that is what we know about just a 2-fluid displacement process. It can be viscously unstable, we're injecting the low viscosity fluid, or we flip it around and it becomes viscously stable and there is no pattern in that system. Okay, so that's with just 2 fluids, and now we're going to add grains into the system. So with just the 2 fluids, we had already surface tension of the meniscus. So we had capillary forces, and there was viscous forces, but now we're adding grains. So now we get friction forces as a third component. So this becomes now a dance between these 3 different mechanisms in the system: the mechanism and the capillary force, the meniscus and the capillary forces, the viscous flow that creates viscous pressure gradients, and the friction, because we have loose grains in the system, that if we try to push them, they bunch up and we get friction where they have to be pushed against the glass plates that's holding. So these 3 mechanisms, and we can define some dimensionless numbers, and we define a capillary deformability as a ratio of the capillary to the frictional forces. And in our experiments that I will show you, we will always be in a situation where the capillary deformability is very large. That means that the grains are loose and the friction is fairly low. In other words, the meniscus is able to move the grains. So it is a deformable medium in that sense. What we are going to pay attention to is the second one, which is the viscous deformability. So this is the competition between viscous forces and friction. That's going to be the topic of today. Now, viscous forces are proportional to the viscosity of the fluid and the injection rate. Friction we can control by controlling this filling fraction of granular material that we have in the cell. So if we put a higher filling fraction, that means there's more effective friction in the system. If we increase the viscosity or increase the injection rate, then we're increasing the amount of, the viscous forces in the system. So those 3 things there are going to be the experimental parameters that we are going to investigate. And then the topic of today is to look at 2 scenarios. First, the viscously unstable scenario. Now, this is work that we did quite a long time ago. This is when the invading fluid has a lower viscosity, So if we're injecting air into a system where there's glass beads submerged in water, for example, that is viscously unstable. So that's one scenario. And then more recently, we have looked at viscously stable scenario. So now we're going to have to inject the high viscosity fluid, and the grains are going to be submerged in the low viscosity fluid. And then we're going to see what that does. So we're going to compare these two things now in this talk. I'm going to first summarize these old results first, and then we're going to get back onto our more recent results. Okay, so what have we done by introducing granular material to the system? We have our meniscus here, and it's a displacement process. And because the capillary deformability is large, that meniscus is going to be able to push against the grains, and is going to push them away, and is going to accumulate a front of granular material here that, as the meniscus is pushed in, grows bigger and bigger. And then we are looking at the friction here. So now we might get force chains inside this packing of particles that increases the normal force on the bottom here. And if we were to take the traditional Janssen law here, that normal force is proportional to the stress or to the force that we are pushing horizontally with there. So in that case, we could get a jamming of the grains inside, inside the gap between these two plates, and that's going to cause an increased friction, and that becomes then a dominating force in this system. So here's a simulation. This was done by Benji. I don't know if you remember Benji, but he was there in Oslo 5, 6, 7 years ago, something like that. And he did this DM simulation of this capillary bulldozing, where a meniscus is able to gather up these grains. And here in this simulation here, we have the walls moving against this wall here, which plays a role of the meniscus. So we are in the reference frame of the meniscus. Yes. And then we were able to, in the simulation, look at the, how the force buildup becomes exponential in this 1D system because of this jamming effect, where the horizontal force you're pushing with gets distributed through the force chains, increasing the stress on the plates. So that is what happens then in a 1D system. And then in a Hele-Shaw cell, we have a 2D system now. And then we have this new pattern forming mechanism, which we call frictional fingering, which is caused by the buildup of the grains that you see here. You can see this dark band surrounding the fingers. The fingers are air that is being pushed in and is pushing the grains away, and it creates this compaction front, which you see as a dark band as it is displacing this grain water mixture that we already have in the cell. So you can see here there is a pattern forming mechanism, and it's creating a natural length scale in the system, which is the finger width. And you can see here that when the fingers meet each other, they stop growing because they can't grow into each other's compaction fronts. That is prevented by the increased friction there. Okay, so this is a frictional instability, which is created by the two forces. And by the way, we are doing this really slow now. So we are not interested in viscous forces at the moment. We are just simplifying this to just look at the surface tension of the meniscus and the friction of the buildup of the grains. And the meniscus acts as a bulldozer or as a snow plough that is ploughing up granular material. But the frictional instability happens because by creating an undulation on the interface is able to push the grains sideways. So it's ploughing them to the side rather than building up a massive compaction front ahead of it, which would be very hard to move because of the amount of friction. So friction would like to create a highly curved finger that would move the smallest amount of grains in the system. But that's where surface tension comes in, because surface tension wants to smooth out any local curvature in the system. So there's a competition between the friction and the curvature, where the total stress, the total pressure in the fluid that is displacing the fingertip has to work against the friction in the system and the surface tension. And the friction and surface tension together creates the total amount of pressure that you need to move forward with this finger. And as you're ramping up pressure, we can sample, the system samples all along the interface, and it will choose, as you keep increasing the pressure, wherever you have the lowest yield stress, that's where it will grow. So the system is always looking for minimizing the stress. In other words, we can take the derivative of this tip pressure, and we can solve for that. And with a linear friction law, as a simplification, we can arrive at the very simple expression for the finger width in the system. And you see that what happens if we increase the amount of grains. So that's one of our three parameters that we are tuning here. If we increase the amount of grains, we get thinner and thinner fingers, and that is because more grains means that to push out, we are working against more and more material, so there's more and more friction in the system that we are having to push against. So the finger width, this characteristic length, is going to be a decreasing function, which you see here, of the filling fraction in the system. But if we were to increase the surface tension, well, surface tension would want to make the fingers wider to reduce the curvature at the tip. So that is what this simple prediction tells us. And those are the results. So that is the emergent finger width, frictional fingering set by a competition between surface tension and friction, emerging as the natural length scale in this system. Right, so hang on. I've gone a bit rogue. Hang on. I'm sharing this from a surface pad, which is typically unstable. Okay, so we're back. Right.
Bjørnar, can I just have a quick question?
Yep.
So just so intuitively again about the surface tension there, if you increase the surface tension, wouldn't the the radius decrease? I'm just like, if you increase the surface tension, then the capillary forces increase as well, right? So you want...
so the capillary forces are, you know, according to your Laplace pressure. If you this is like an effective surface tension, effective capillary pressure, where the fingertip has a radius of curvature r. So if you think of the finger as a pore, then the wider the pore, the lower the pressure you need to invade that pore. Right? So essentially, that's the same as saying that the surface tension energy is minimized by making that curvature as large, the radius of curvature as large as possible. In other words, straightening out the finger. So if you were to increase the surface tension would work against having narrow fingers, because a narrow finger has a very sharp curvature tip. So the surface tension always tries to kind of widen out the fingers.
Right.
Is that all right?
Yeah. Super.
So,
thanks.
Yeah. So right now we are just looking at the simple case of just surface tension and friction, and together.
Excuse me.
Yeah.
I have something I wonder about here. This is
Yeah.
this is Per. When doesn't the filling fraction phi change as you start pushing air into it? Presumably, it's like snow plow. You will get big, so that it would fill. I would think the filling fraction near the interface would go to 1.
Yes, yeah, that's exactly what happens. So what you see here, so we're doing this very slowly, which means that there's no viscous flow, the flow throughout the cell. We're injecting air here, injecting air into the system. So it's dripping out water or water glycerol at the open edge of the cell. So we are pushing that away, but that flow does not move the grains here. So they are all just sat there, waiting. And then comes the finger. And the finger is acting like a bulldozer. So if the filling fraction, let's say, was 0.5 initially here, locally here, we call this filling fraction is equal to 1 because we get this localized compaction from it. Yeah.
Okay,
so,
I
but all of this, but it becomes, it's very, when you look at the system, at the pattern, it's very homogeneous because we don't have grains pushed around everywhere in the cell. So locally, nothing happens until the bulldozer comes and reorganizes the grains locally. That's why it looks the same everywhere in the cell, and we get this characteristic finger width that is uniform throughout the system. Now, that's not true once we start to increase the injection rate here. Then we start to push grains around in the system, and I'll show you that later on what that looks like. But yeah, so it's all about the local compaction. So it's that is what creates this frictional instability. Okay, this is just to zoom out. We are interested in this. In this talk, we are going to be talking about the fingers the whole time. But, if we were to increase the filling fraction quite a lot, then we get to a point where we get capillary fracturing. So now, this is kind of a different, it's similar, but a different mechanisms where the fingers are no longer finger-shaped, but they are in more this kind of fracture shape. And now we do have pore invasion happening. When we have the fingers, remember, we are in the capillary deformability that is so high that the meniscus is always able to push the grains, and the meniscus never goes in to the pore space between the grains. So
in that sense, the interface is pinned at the
it's always a case here that if these are the grains of the meniscus, the interface is always here, and you get an accumulation of grains, but the pressure in the fluid is never close to the pore invasion pressure of the the accumulated front. But that is what is different in this system. In this system, you have a fracture, but at some point, the pressure, you're pushing so much material to the side that at some point, the pressure in the fluid has to become so high that you actually get pore invasion events. And that is what triggers the new fracture to grow. That's kind of the difference between these two systems. If you were to go even further and have a filling fraction is equal to 1, then you just have that is just a porous medium.
Yes.
So that is porous, that is pore lab territory. And if you go all the way to a filling fraction is equal to 0, well, then you have no grains in the system. So now you're back to the situation that I described earlier, where you just a displacement between two fluids. So our frictional fingers are existing in a range of filling fractions where the capillary deformability is high. In other words, we can easily push the grains around and create fingers out of them. Right, but this is what we will be talking about, the fingering system. Okay, we're still in the viscously unstable situation where we're injecting the low viscosity fluid air into the defending fluid, which is higher viscosity glycerol water mixture containing the grains. We've seen that at very low viscous deformability, when we pump in very slowly, we can neglect the viscous forces, and it's just surface tension and friction that creates the frictional fingers. But what happens if we increase the viscous forces in the system now? So now we're injecting faster, and now it's a much higher viscosity. That is a water glycerol mixture. So now something else is happening. This is actually very much similar to the viscous fingers that I showed you for just a two-fluid system. So what is happening in this system here is that the grains become fluidized. The grains are submerged in the high viscosity fluid. So if you push too fast, then the grains become fluidized, and they're just carried by the fluid. And at this point, it's almost like you're just pushing effectively a granular suspension. So that is turning off the frictional instability. When the grains become fluidized, we no longer have this frictional jamming inside the cell that created the frictional fingers. So we're turning off the frictional instability, and instead what we get is the viscous instability, because this is a viscously unstable system. So that is kind of a summary of what happens in the, I guess the summary comes here. We have now looked at viscously unstable pattern formation in frictional fluids. Well, in viscous fluids, we get viscous fingering, and if we add grains to the system, we get frictional fingering when we keep the viscous forces negligible in the system. But once we start pushing very fast on the system, we get a transition to viscous fingers because we turn the frictional instability off by fluidizing the grains. So that is a scenario there. And now we are going to look at a viscously stable situation. So now we're going to flip it around. We are going to inject the high viscosity fluid. And so in this scenario here, we are injecting water glycerol, and the pink fluid here is air, that side. And if there was only fluids, there would be no patterns. We would just have a disc that would expand radially, stabilized by the viscous forces acting inside the invading fluid. So now what's going to happen if we add grains to the system is the question. It could get really boring. We could just get a situation like in the picture above where there's no pattern formation at all. So that's a risk, but let's see what we get. Okay, first, how are we going to do these experiments? We're going to have air as the defending fluid and water glycerol as invading fluid, but we still want the grains to be wetted by the defending fluid. And the defending fluid is air. So we're going to have to make the grains hydrophobic. Okay? So you can play with the hydrophobic grains that you buy in a toy shop. And you can see when you do that, that you can put it in water and it will clump together. That's the hydrophobic wetting of the grains prevents the water from penetrating into the pore space. And when you take the grains out, they're all dry inside, right? So that's the kind of situation that we want. We want the water to come in and push the grains away and to have no penetration into the pore space, just as we talked about before, where the meniscus is pinned by this by the grains at the surface. We don't buy it at the toy shop. We silanize the grains ourselves with a chemical procedure, but we end up with hydrophobic grains that are exactly the same as in the other experiment I showed. So we've swapped the viscosity ratio, and we've also swapped the wetting of the grains around. So we're ending up in exactly the same scenario, in drainage scenario, where the only difference is that this is now viscously stable because we're injecting here the high viscosity fluid. We still get an accumulation of this frictional front, and it's still the friction in this front that should set up this frictional instability that we talked about. And if we do this very slowly, we get frictional fingers still, exactly the same as before, or more or less the same as before. Again, we have a finger width that is set by the competition between the friction and the surface tension in the system. And we can show the video, I suppose. So here's a very slow injection. So essentially my message here is that when we're doing it very slowly, there are no viscous pressure gradients, neither in the, not in the defending fluid and also not in the invading fluid. So at that point, there's no difference really between the two systems. We get frictional fingering. It's set by the competition between those two forces, and viscous forces play no role. But what we are interested in now is, of course, the effect that swapping the viscosity ratio is having. So what we're going to do now is increase the injection rate and keep pushing on the viscous forces until something happens. And then look at what that might be. And this is what happens. So now we're injecting faster. This is still water that is being injected. So the white, this here, is water, and this is grains in air. And you see the dark band that forms around the fixtures, well, that around the fingers, that is the compaction front of dry hydrophobic granular material, where, as we talked about before, the filling fraction is 1 locally, and out here it is 0.5, right? So exactly the same as before, but now the thing that you notice when you're doing the experiment, the difference between low injection rates here is that there's like one active finger typically in the system, and in increasing the injection rates means that there are now more active fingers. So there's a number of active fingers N that we have to understand how that comes about. So we can go from one finger, increase the injection rate a little bit, and suddenly there's 2 fingers. Increasing a bit more, and there's 3 fingers. And then there's 4, and then there's 5, and then there's an increasing number of fingers that are active in the system. And this is in response to us increasing the viscous forces in the system. So to understand this, we have to just remember that now the viscous forces are located inside the fingers. So when we're pumping fluid through those fingers and it's growing at the tip of the finger, this is where it's growing, there is a flow of the viscous fluid through that finger as if it's in a pipe. So you're pumping the fluid through the pipe to get to the tip of the finger. At the tip of the finger, you have, as before, you have your friction and your capillary pressure and your capillary forces at the tip. But if you were to start from the tip and you're walking backwards, it's like walking backwards through a pipe, the pressure in the fluid is increasing gradually the further back you get. And that is because of the viscous flow, which is essentially like a Darcy flow through this finger pipe in the Hele-Shaw cell. So the pressure that you need to pump at to keep a steady injection rate, that will keep increasing the longer your finger becomes, because you have to compensate for all the viscous dissipation for the flow throughout that finger. Okay. Now, we can model this by saying that we have our injection rate. Now, the width of the finger is 2RF, and the cross-sectional area is multiplying that by the gap thickness, the Hele-Shaw thickness. So this here becomes the velocity. And if we're interested in the average velocity, then we can divide by the number of fingers. And that's given by Darcy's law here. So here's your permeability, or viscosity, and here's the pressure gradient. So here's the pressure across a length of finger. So if this is the kind of length of this finger, delta RB, then this is the pressure gradient, delta PV. It's a pressure gradient from inlet towards the fingertip that we've got. And now the question is, when is this going to sprout a new finger? We have seen that we can go from one finger to having multiple fingers growing simultaneously. And we can do this by increasing the injection rate. And that is having the effect of making that pressure gradient steeper inside the system. So if we pump faster or we increase the viscosity of the fluid, we get a steeper pressure gradient. And the question is, at what point is that pressure in the fluid going to overcome that compaction front strength that we have built up? Remember, we have a compaction front of granular material. That is a wall surrounding this finger. And when we get a new finger sprouting, that is because the fluid pressure is able to overcome the strength of that wall and break out and form a new finger. So we have a viscous pressure in the system. And the question is, when is that fluid pressure going to be higher or equal to the strength of the wall? And that becomes a criterion for when a new finger is sprouted. So we're going to try to understand the number of fingers as a function of all the parameters in the system. And it is natural that the breakout happens at a distance, delta RB, when the fluid pressure is able to overcome the strength of the wall and break out. So back to our viscous deformability, that is the ratio between the viscous pressure and the frictional strength. We can define this viscous deformability in a way that it becomes, there's a critical viscous deformability that happens when the ratio of these two are equal to one another. And we can define it such that we get, well, if the viscous deformability is low, then one finger can get all the way to the edge of the cell without breaking out a new finger. But at the critical viscous deformability, just before it reaches the edge of the cell, we get n going from 1 to 2. That becomes our criteria. Mm-hmm. We're asking the question, what does the viscous forces have to be in the system to just be able to create a second finger before the first finger has reached the edge of the cell? So delta RB should be the system size, and the number of fingers should be 1. That becomes our criteria. All right, now we have said already this is a cross section of, so if you have a finger here, so your 2RF is the finger width, and then it has got a gap thickness B. So 2RFB, that is the cross-sectional area here. And the length of the finger is delta RB before we are sprouting a new finger. So the volume here, inside here, is the volume is your 2RFB. Oops, delta RB, that becomes our volume. So that is the amount of volume that we have to inject to create one more finger sprouting out, because that's when the viscous pressure is able to break out. So this is the volume that we need to create, to inject, to create one more finger. And if we pretend that the fingers are continuous, not an integer number of fingers, but a continuum, and we integrate that up. And now we have a model for the number of fingers that is a function of the volume we inject. Because to begin with, we're injecting fluid, but the finger needs to become a certain length for the fluid pressure to increase to the point where it can break out the new finger. It is a function of our viscous deformability. Our viscous deformability is just the viscous forces, so it's the viscosity, multiplied by the injection rate. And it was a ratio between the viscous forces and the frictional strength of the wall, remember? So we can increase the viscous forces, either viscosity or injection rate, and that is going to create a steeper pressure gradient through the finger. And that means that we are going to break out the finger at an earlier, at a shorter distance away from the tip. So our number of fingers is predicted to increase with the volume and with the injection rate, and it's predicted to decrease with the frictional strength, because the stronger the friction is, the harder it is to break out a new finger. And now we can compare that to our data. And we see here, if we plot the number of fingers in the experiments against the injection rate, this is like time. It's like the injection rate multiplied by time. That's the injected volume. Then we see here increase in the number of fingers. That looks like a square root. So that's a check for the model. We see that if we increase the injection rate, well, that's also predicted by our model here, because we get a steeper pressure gradient. So that's gonna, get more fingers to sprout more quickly. On this graph here, we are increasing the filling fraction, and now we get fewer fingers. So if we have a system with more grains in it, then we get fewer fingers. And why is that? Well, that is because we have increased, therefore, the frictional strength of the wall. So it becomes harder to break out new fingers. So this makes total sense. And the only unknown that we don't know in this system is really how should we model this frictional strength of the walls? And we have a reason to suspect that this is an exponential model because of this, the jamming, the force chains that causes an exponential increase in the amount of force that you have to push, the thicker that compaction front becomes. So when we were to plot, so now we take all of these lines and we fit them with only delta PB being the free parameter. And if we were to then plot delta PB, that gives us the best fit. This looks like a straight line on a log lin plot. So we take that as confirmation that our exponential friction law for the sides is working pretty well for us. And we just use this curve up there to fit that only free parameter, that sigma beta there. Okay, that's it. So that's our model for the number of fingers, and we can see a reasonably good, well, I don't know if you can call it a collapse, but all the data gathers on that line here, which is according to our model. So that is fine for us in a reasonably small number of fingers. This breaks down because of crowding out the fingers as we go further in terms of number of fingers, but that's not part of this model, so that's not included. Okay, I'm going to speed up. We can simulate the thing, and the only difference between our new model and previous models is that we've skelenized the fingers, and then we're just solving Darcy's law on a flow through that finger skeleton. So now we have viscous pressure, and we have friction and surface tension as before. So a simple model like that, and this is just to show that the model is able to reproduce this pattern formation that we see, where in exactly the same way, or in more or less the same way as the experiment, we increase the number of fingers as we increase the injection rate of the viscosity in the system. Okay, that all of the data that I've showed you now is injecting water. And then later on, we decided, let's go all out on this and increase the viscosity. Let's see if we push the viscous forces to the extreme, what will happen. So here is an experiment with pure glycerol. And we are basically injecting as fast as the syringe pump is able to cope with this. And now we get a new pattern forming. So this is what we call a spoke pattern. So now you can really start to see this viscous stabilisation in the system, where it really wants to create that viscously stabilized growing disc that we saw for just a two-fluid system. But the frictional instability is not turned off in this system. The grains are in the low viscosity fluid, so it's very hard to fluidize the grains. Therefore, the frictional instability is always acting, and the viscous stabilization has to map on top of that frictional fingering instability. And it does that by creating a fully compact spoke patterns where the fingers are growing side by side in this pattern that you see there. And then we tried the simulations, and straight out of the box, it did exactly that, which was a very nice surprise, because that doesn't usually happen. But the simulations are exactly reproducing this pattern forming mechanism. And if we were to plot this on a phase diagram, now we have the viscosity here in the injection rate. Remember that our dvisc is proportional to viscosity times injection rate. So if we were to plot the viscosity, well, that's just, so my point here is that we get it's just a 1/q, and this is a log-log plot. So a critical viscous deformability here becomes a straight line. So essentially, it doesn't matter if we increase the viscosity or if we increase the injection rate. As long as we keep the viscous deformability number the same, we get the same pattern. And it goes from one finger to multiple fingers to spoke pattern, where the spoke pattern is a fully viscously stabilized pattern. Yeah, I think that's all. Yeah, this is growth from one finger to two, and this is the spoke pattern. The characteristic length there, we say, is when a finger breaks out a new finger already, within the characteristic length scale of the finger pattern, which is your 2R, which is the finger width. So I'm going to move quickly past that, but so those become two critical viscous deformabilities: transition from one finger to many, and from many fingers to a fully viscously stabilized system where the fingers are growing side by side and a fully compact pattern as a result. Finally, we are increasing the the filling level. And now we see that if we start out with a spoke pattern, gradually we're going to break up that spoke pattern until here. You couldn't say that that was a spoke pattern anymore. And what's the reason for that? It is because now, really, the viscous stabilization mechanism is competing against the strength of the walls. And if you're increasing the strength of the walls, then that becomes more important compared to that viscous stabilization or the viscous pressure gradient in the system. So you can kind of go back. So, as a conclusion, if we increase the viscous forces in the system, we can go from one finger. Viscous stabilization acts to break out new fingers. That is how it tries to become more and more viscously stabilized. The frictional instability you can't get rid of. So the only way to viscously stabilize the system is by breaking out new fingers. And in the end, you're breaking out new fingers at such a rate that the length scale is like on the length scale of the fingers. But if you go in this direction, you're increasing the strength of the walls that you have to break out of. And that makes it harder and harder to break out these new fingers. So we can kind of reduce the number of fingers by going from left to right in this case diagram. And that's my conclusion. So we can replot this, I suppose, on the viscous deformability parameter that we just defined. And that's what the system looks like. But the conclusion is the same. Increasing the viscous forces tries to make the system viscously stabilized, more and more compact. That's what its job is. Frictional fingers are always here. And the more friction you put in the fingers, you're going to prevent, you're making it more and more difficult to have this breaking out the new fingers because the strength of the side walls are increasing. And that takes you then going in this direction in the case diagram towards a smaller number of fingers. And that's it. So in the first system we looked at, where it's viscously unstable, we get the frictional instability at low rates. But if we increase the viscous forces, we fluidize the system. So we kill the frictional instability by fluidizing the grains. That is the mechanism there. In a viscously stable system, the grains are always in air, in the low viscosity fluid, so they don't become fluidized. Therefore, we always have the frictional instability, and the viscous stabilization effect is always mapping onto it. It's trying to create more fingers, ultimately creating a fully compact spoke pattern. So that's basically what we know to date. Yes, that's my conclusion.